This lecture looks at VLANs and gives an introduction to some of the fundamental areas related to VLANs. One of the most basic concepts is the idea of a broadcast domain, and it's the thing that makes the internet so dynamic in that hosts can join the internet, and it's ARP that allows other nodes to be able to find them for the last part of the network. Basically, if one node wants to find the MAC address of another node that it knows its IP address, it sends a broadcast ARP packet to the whole of the network subnet. So in this case, all these nodes will receive the ARP packet, where this node asks for the MAC address of this node. When this node detects that it is its IP address, it returns back only to the node which requested it its MAC address. When that happens, the ARP table on the host that asked for the MAC address will update its ARP table. In this way, we can dynamically add and delete computers from the network. After a while, the address mapping is aged out of the ARP cache and the host must re-ask for it. So if a node goes offline, then it will need to be requested again. Basically, a network bridge, which works at layer 2, will forward any broadcasts on to another network. And basically, any node within inside of the broadcast domain can see any other node and find it. So a bridge extends a network segment. A router, on the other hand, will block any ARP and broadcast traffic. So these nodes cannot communicate directly and find each other's MAC address. There is also no need for it. It is up to the router to be able to route the traffic. Repeaters also extend the network segment, basically cleaning up the signals, multiplying the signal strength and resynchronizing. The bridge also in this case will forward ARP broadcasts along here too, but they will be stopped by this port. Also, the router only forwards for a network segment which is on that segment. If we see here the extent of a broadcast domain, we see nodes A to K. A and B are in the same broadcast domain because the broadcast will be stopped by this port on the router. A hub forwards broadcasts, so it will go to C, it will also go to E, but it will be blocked by this port here. F will go through the switch will forward on through the bridge to G and also to H, but the broadcast will be stopped here. And the repeater also forwards, so it forwards it to the switch which connects to J and K but is bounded here. So the ARP only applies within inside the broadcast domain. Nodes within inside that broadcast domain can connect directly to other nodes because they can actually discover them within inside the broadcast domain. Here we see a hub, and the hub connects the broadcasts. Okay, so how does the internet actually work, and how is it that computers can add and delete themselves from the internet and other destination nodes can find them? Well, basically, when this machine wants to talk to this machine, this machine does not need to know the MAC address of the destination. It would be too difficult for it to find that out. So basically what it does is it puts its own IP address in the source and the destination IP address of the destination node. Then it adds its own source MAC address, and through ARP it has already discovered the MAC address of the gateway. So the first data frame that goes out has the destination MAC address of the gateway port of the router. The router then knows the best route to get to the destination. It will then forward the data frame over, this time using the source MAC address here and the destination MAC address of the next gateway. Again, the IP address doesn't actually change. Then this router then forwards that on, and the data frame that's transmitted has a source MAC address of MAC5 and a destination of MAC6. Only when it gets to the last network does the actual MAC address of the destination node need to be resolved. In this case, we can then communicate directly with this host because we have the correct details for its MAC address and for its IP address. And it's this magical last segment where we can resolve the MAC address that makes the whole thing work. So typically we go through the internet using routers. Each router typically takes up to layer 3 and then forwards on. So the key thing that any node, when they wish to get out of a local network, is to broadcast for the default gateway MAC address. So typically the IP address of the gateway is defined on the computer, and then an ARP is used to discover the MAC address. Once those are determined, then it is possible for the host to be able to connect to an external network. Basically, ARP here allows the gateway to determine the MAC address of the actual destination. Same again for the intermediate devices, they discover each of the gateway MAC addresses by an ARP. So ARPs stay within inside each of their subdomains. This lecture focuses on the Cisco BC MSN certification and provides a basic introduction to switch networks. The main areas that we'll look at as part of the certification includes the span entry protocol, multicast and general availability, VLANs, trunks and VTP, quality service, multi-layered switching and security. The first part just is a basic introduction to switching. Basically, we're moving away from older network structures where 80% of the traffic within a network was typically local, and only about 20% of it was destined for other networks. These days, much more traffic is destined for external servers, such as on a server farm or a DMZ, or for the internet. So much more, there is a move towards 80% of the traffic being destined for other networks and only 20% being local. So this leads to the 20/80 rule as opposed to the 80/20 rule. Newer networks are now also based on a switched infrastructure. Basically, most medium and large scale networks are based on a 3-layer architecture. At the access layer, the user accesses the network typically by connecting to a switch. This provides local access, and nodes within inside this domain can typically communicate with each other. The main difference though is if we create a VLAN, then the nodes can be isolated. At the layer above, we have a distribution layer where we distribute the connections between various switches. So we can now get intercommunication between devices which connect to different switches. This can operate at layer 2, which is the most efficient layer to operate at and can be switched, or it can operate at layer 3. So this layer we see either layer 2 devices to switch, or we see layer 2 stroke layer 3 devices which can route at layer 3 level. At the core we have the main connectivity to the main switching networks. The reliability of each of the layers should increase as we go through. The core layer should be the most reliable of all, followed by the distribution layer and then the user access layer. The network bandwidth that it supports will typically also increase. If we have 10 megabits per second here, then we typically multiply up to 100 and then on to 1 gigabit per second at the core layer. So at the access layer, we typically get user or device authentication onto the switch. We have VLAN membership, where we can define the VLAN number that a host might be connected to. We can filter on basic MAC addresses, and we can also now define the quality service for each user or each port on the switch, where we might give high priority to one node and a low priority to another node. At the layer above, we can interconnect between work groups. We can then interconnect between VLANs. So if this node is on VLAN 1 and this node here is also on VLAN 1, this node is on VLAN 2, this node is on VLAN 2. With VLAN trunking, we can create a connection, a virtual connection almost, between the two VLANs which are the same. So in this case, these two nodes would seem as if they're on the same network, along with these two nodes which would be on another network. If we need these machines to be able to intercommunicate, then we use a layer 3 interconnection. We can also define security policies at this level, typically defined at a layer 3 access, where we can define the traffic that's allowed to flow from one VLAN into another, or from one network subnet to another. We can also have network type translation at this layer and address summarization, typically in layer 3. At the core, we typically get inter-site and inter-campus connections and also external access. The typical switches we see at each layer is a Cisco 1900 Catalyst switch or a Cisco 2900 Catalyst for access. For layer 2, layer 3 switching, we typically see a 3550 Catalyst switch, and for the core of the network we look at robust, highly robust switches such as the 6500 Catalyst. We see here an example of a network where we have access layer, and as we'll see, we can have failover routes that interconnect, so that if one of the switches fails, we have an alternative route to another switch. So we have distribution here, and then this gives us core, and we can see we have some routers which allows the interconnection between different networks. The 2900 is used here, the same with the distribution layer, and a 3500 is used for a core layer here. For the basic configuration, we typically have many ports on a switch. In this case, we have 24 ports from FA0/1 to FA0/24, and we also have 2 gigabit links. By default, we create one VLAN which is named VLAN 1, of which all the ports can be associated with. Normally, if we operate at layer 2, there is no IP address associated with the interface. But we can use a web server to be able to connect to the switch. If this is the case, we need to assign VLAN 1 with an IP address. It is this IP address we use to remotely access through Telnet or through the web. Telnet access is with the VTY and a console port is through Con0. We can see here that all the ports have been enabled, and they are typically enabled by default. VLAN 1 though, you can see, is in the shutdown condition. So if we need to define remote access, we define an IP address for the switch, in this case 192.168.1.100. The switch's ports themselves do not need an IP address because we do not need to access them individually, we just need to access the switch. Some switches, such as the 3550, are layer 2, layer 3, so they can either operate at a layer 2 level or they can work at a layer 3 level. In this case, if we wanted to make the Ethernet FA01 port a layer 2 port, then we define the switch port mode access. To define a layer 3 port, we say no switch port mode access. This will allow us to work as a layer 3 port for routing, and we can apply an IP address onto it. If we want to trunk between VLANs on a switch, so from one switch to another, we need to enable a trunking port. Then the VLAN traffic will travel along the trunking port to the other switch, which will then be able to connect and join up the two VLANs. In this case, the first port is defined as a trunk port. And if we want to define a port as part of a VLAN, we say switch port mode VLAN and then the number of the VLAN. A VLAN with a number of 2 with trunking enabled will connect to another VLAN with a number of 2 on a different switch, as long as there is a trunking port defined. And that's the end of the introduction to this. Okay, so let's look at one of the most basic levels of security, and that's layer 2 security, looking at VLANs or virtual LANs. So what is a virtual LAN? A virtual LAN involves creating a logical network. In this case, all these nodes connect to the same switch, but we can segment them so that certain ports connect to one VLAN and other ports connect to another VLAN. The two networks cannot communicate directly through the switch. So in this case we have PC 9, 16 and a server connected to one VLAN. This defines the scope of the broadcast domain, and then PC 1, 8 and server 1 connect to another VLAN. So in this case we can apply security at the very lowest level. So why do we use VLANs? Well, VLANs allows us to create networks across multiple switches. We can see here that these machines need to be connected together in one LAN, but this machine connects to a different switch. Through trunking, it is possible for us to span VLANs across switches. So now, even though these three machines connect to the same switch, they are not connected to the same network. Again, VLAN 2, we can span across the various switches. What we need is a trunking backbone. And basically what will happen when a broadcast happens from one node, it will be sent to all other nodes in the VLAN and not to another VLAN. So it will be sent across the trunking route to the other switch. Same again, a broadcast here will be sent to this node through the trunk and then also to that node. So an example of VLANs is implemented in a switch or in a Cisco Aeronet. So the advantage of VLANs is that we can set up microsegmentation, where we can split the bandwidth up into smaller and smaller elements. We have enhanced security, where we can isolate one part of the network from another, even though machines connect to the same switch. We can relocate servers away from local machines and put them into places like server farms, but the hosts still stay connected as if they were connecting to a local LAN. And it allows us to create subnets very easily. Along with this, we can create virtual networks, and it should help to ease administration in that we can move resources wherever we require them. Along with this, it improves the bandwidth usage as network traffic stays within a certain workgroup. If we have a great deal of local traffic, such as to servers or disk farms, we can keep it local within inside the same VLAN, and it doesn't affect other VLANs. Okay, so let's see how we configure our VLANs. Basically, there are two types: a static VLAN, where nodes are permanently assigned to a VLAN, typically depending on the port that they actually connect to. We can also have dynamic VLANs, where a user or a certain machine, no matter which port on the switch they connect to, they will still connect to the same VLAN. For this, we need a database which defines the VLAN that users or nodes connect to. Typically, it detects a MAC address to assign the VLAN. Static LANs are extremely secure, and they need to make sure that a certain machine connects to a certain port. So for static VLAN, what we have here are two nodes that connect to the same VLAN, and we have two other nodes which connect to the second VLAN. These ones connect to VLAN 1 and these ones to VLAN 2. So what we do is that we create our VLAN. VLAN 1 is normally created anyway, but we create it with interface VLAN 1 and we enable it with no shutdown. We create VLAN 2 and again we enable it. Now we can assign each of the ports to the VLAN. So switch port access VLAN 1 will assign this port to VLAN 1. For the third port, we assign that to VLAN 1. So now these two machines are in the same VLAN and can communicate directly. These two interfaces are then connected to VLAN 2, so these two can now communicate. If we try to ping from this machine to that machine, we can see that it is successful. But if we try to ping from this machine to this machine, then it is unsuccessful, as we can see here. The only way that these two devices can actually communicate is through a layer 3 device. The basic VLAN types that we have is that we can allocate it by port on the switch. We can define MAC-based VLAN. Depending on the MAC address, it will assign it to a certain VLAN. We can define it for protocol such as IP or IPX. In a wireless system which has multiple SSIDs, we can assign each SSID to a certain VLAN. That allows us to span across various aeronets and still connect to the same VLAN. And we can also have ATM VLANs for switching ATM cells. In a dynamic VLAN system, we need an MPLS server, typically run on a 6000 series switch. And this device actually contains the database which maps the MAC addresses to the VLAN numbers. So in this case, we define our VLAN and we give it an address. The reason we give it an address is it's so that we can access it remotely to be able to configure it. Then we say that the VLAN allocation is dynamic for the two ports that we have here, 1 and 2. And then we define the VMPS server. In this case is the .2 machine, which is the switch. As this is so important, if there was a failure on the switch, then we typically define a secondary VMPS server. So in this case, this is the primary, and the system will try this switch first. If we define a secondary, then it would go to the other machine. We can have a reconfirm and a number of retries. If it doesn't manage to contact it, it will try again for up to 3 times. The reconfirm will go back every 60 minutes in this case and reconfirm the allocation of the VLAN just in case that it's been allocated to another VLAN. So these commands define the VMPS server for reconfig and retry, and then when we say show VMPS, it shows us the basic details of the VMPS server. On the VMPS server, we typically have our configuration on a TFTP server, and when the machine is booted, it loads up the VMPS file, defines the domain, and then defines the mapping of, in this case, the VLAN name staff is allocated to this IP address, this MAC address, and students is allocated to this MAC address. So in this way we can allocate our VLANs in terms of a VLAN name. So with inter-VLAN, we need to be able to send our VLAN information across a trunking route so that we can join up our nodes across multiple switches. So we typically reserve one port on each switch purely for a trunking route. We can also do layer 3 with a layer 2, layer 3 switch, so that this machine can actually talk to this machine, but only through a layer 3 interface. And at layer 3 we typically define firewall rules to either block or allow traffic at layer 3. We can see here an example of between a switch and an aeronet, where we can have various SSIDs. In this case, this machine connects to VLAN 1 SSID, this is VLAN 2. Then through the switch we can map up machines that are connecting to a fixed network and become part of the same VLAN. Okay, so let's look at some more VLANs. The trunking protocol that's used is 802.1q. 802.1q is enabled to allow the trunking to happen, and basically it adds extra information onto the data frame which tags the VLAN that the node is in. So we have a normal data frame, it goes through the switch, 1q adds this extra information to define the VLAN, goes across the trunking route, the switch picks it up, strips off the VLAN information, and then is sent to the required node within that VLAN. So basically the way that it's done is that in the Ethernet frame we have some preamble, a destination MAC address, source MAC address, and then we have Ethernet type. At the end we have a basic check sequence. Then in between we have some data in here, which can be up to about 1500 bytes long. About 1516 bytes is around the maximum length of a data frame. So when we carry ARP traffic, we should see the value of the hexadecimal value of 0806. If it's an IP packet, 0800. If it's a 1Q tagged, we should see the ether type of 1800. So we can see here an example. This is an IP data packet with inside our Ethernet frame. So here we see the destination MAC address, here we see the source MAC address, and then we get an ether type of 0800, which is an IP packet. So the way the encapsulation is done is that if we have our ether type of 1Q, then the bit that comes after it is then added. We can have 8 levels of user priority, a CFI bit, and then we can have a 12-bit VLAN number. 12 bits allows us to create between 0 and 4095 VLANs. So the maximum number of VLANs that we can have on a site is 4096, which should be enough for any network. The Ethernet type is then just added at the end of this, so that when the data frame is recovered at the other side, the red parts are taken off and it recovers the original Ethernet frame that originated on the original network. So this is defined as an encapsulated data frame. So we can see here another method is an ISL trunk, and this is less used these days because this is a Cisco derived protocol and it doesn't embed into the Ethernet frame as 1Q does, but it adds an extra header. For compatibility reasons, this is also supported on many switches. We can see here when we define our trunk, we say encapsulation and we can make it 1Q, ISL, or it can negotiate between the switches on the best type of encapsulation used. So how do we trunk between our VLANs? So in this case we have 2 nodes connected to one switch, 2 nodes to another switch, and we're using the third port on each switch as a trunk. So we set up a connection between the two on those ports. So we can see here that we define that our 2 VLANs, and we can assign them with different IP addresses to be able to communicate with them. Port 1 and port 2 on this switch are used as layer 2 access, and then then the third port is encapsulated with 1Q. It then defines the native VLAN, which means that the data frames are not tagged, and then it defines the VLANs that are allowed to be trunked. And in this case it's non-negotiable. So now we have a trunking route between the 2 VLANs. If we wanted to assign this one to VLAN 1, then we would use the VLAN assignment here for VLAN 1 and then here for VLAN 2. So this shows an example of VLANs. We would set up on this AeroNet trunking route to the switch, trunk here and a trunk here, and then all these nodes can connect to the same VLAN. So on a wireless access point we can define the SSID that we're going to allocate. In this case we have an SSID of Scotland. We assign that to VLAN 1, and for England we assign it to VLAN 2. And then what we do is that we define a sub-interface for these VLANs, which provides two virtual interfaces, and we say for the radio port .1 the encapsulation is 1Q, and the same again for the other radio interface. We have a .2 sub-interface, and that's allocated to the second VLAN. So nodes which connect to this SSID will be allocated to VLAN 1, and for this SSID will be allocated to VLAN 2. Then when we look at our VLAN information within inside the AeroNet, we can see that we have two virtual interfaces for our connections using 1Q encapsulation. On the switch, in this case we set up our two VLANs and we create them here. There's no need to allocate an IP address if we don't need to access it remotely. And then in this case the first port is allocated as a trunking port, the second one for trunking, and the third one for trunking. So it trunks in between the AeroNets. Okay, so this is a similar example, VLAN 1 and VLAN 2, and this shows our encapsulation. An important protocol that is used in switching is VDP, and VDP is important as it radiates information about VLANs across trunk routes, so that it is possible to discover the whole of a network and find out where VLANs are across these trunks. So VDP also allows us to be able to add and delete and change VLANs within inside a domain. So to create this, we create our VLAN database, define the name of the domain, and whether our device is a server or not. Various applications of VLANs. As we've seen, we can connect wireless access points into the same VLAN as we have here. Then we can have layer 2, layer 3 switching in between, so that we can actually interconnect devices through the layer 3 switch, or we can block communications at layer 3. And that's the end of this presentation.